Okay. So thank you everyone for coming tonight on the topic of Intro to Hawaii Soils and Tropical Soil Fertility. So yeah, I'm Josh Silva, part of the UH Cooperative Extension team for edible crops. And yeah, we'll get right into it. So to begin, on soil diversity or soil fertility, you first have to understand our unique Hawaii soils because we have very interesting soils compared to other parts of the world. So it all starts a long, long time ago. Like that song says, there was a volcano, and that volcano created parent material. So it's all the minerals, all the elements that come about from a landscape, at least here in the tropics and in Hawaii. So that's what we call parent material. In other places of the world, they might have more sedimentary rock parent material or granite or quartz, but for here we have mostly basalt rock. And once that develops and you have orographic lift and rain and wind, the climate starts to erode and transform those minerals into other parts. And depending on the topography of the land, some might stay on a high point, or if it's the slope is steep, it might go down into the valley bottom. And this all influences how nutrients eventually end up and how minerals form in a landscape. And eventually there'll be some plants that come about, whether it's ferns or ohia, as well as animals, and they bring organic matter, biota, over time, and that influence how the rocks and the soils develop too. And being an island chain, we know that some islands are younger and older than others, and all these other four factors, take time to break down the rocks into the minerals that we know in the soils. So the longer and a place is exposed to these weathering factors, the more developed the soil will become. So you can see here clearly on this soil map of the at least four of the eight Hawaiian islands, where you can see the older Kauai Island, much more developed soils compared to the younger Hawaii Island. And Maui is kind of interesting, where you can kind of see the difference between the older part of Maui versus the younger part. So Lo'ehu na Lepo Hawaii. So very diverse and colorful are the soils here in Hawaii, where it's not all one color, it's not one shape. So you can visibly see this, the color and the textures in the different kind of soils, the reds and the darks and the rocky and the grainy and the gravelly. Um, and using these observations, we can classify them so that way we can kind of group things together and know how certain things behave similar to others. So in Hawaii, we have our way of categorizing soils. So they have, simple words like ula for red or palolo for clay, momona for fertile, for stony, or akeke for cindery. So they had their ways for classifying soils. But in like a more conventional or modern classification system, it follows like scientific nomenclature. So you're familiar with the way that animals and plants are named. We also have a similar method for soils. So we have a broader classification called the soil orders. So these are the oxasols and the andosols that kind of indicate what that soil behaves like. So oxasols sound like oxides. So it has this red thing in nature. Andosols, they're more, they come from a Japanese word ando, which means like black earth, and that's typical of anywhere that has volcanic ash minerals in their soil or heavy presence. And you can keep naming, I guess, getting specific in the names, but the most specific is actually a place name. And here in Hawaii, we have about, I think, like 200 or 300 different series for all the different places, and that's how many unique soils that we have. And going back to in the orders, we have at least 10 of the 12 orders in the world. The only ones we're missing are the ones for that, like in the glaciers and the tundras, the frozen soils. And then there's another soil in between that we might be missing, but we haven't classified all the mountainous areas, and it possibly could be up there too. And these differences in soils, the way they've weathered and been exposed to those kind of mineral weather forming factors, you can see they also have different behaviors and mineralogy. So these are just some examples of some of the mineralogies that are found in these soil types. You can see that they're different and they behave differently. Some can hold more nutrients and water, while some are more stable. So it's just very interesting all the different kind of soils that we have. And being the topic of soil fertility, we can see it clearly in soil fertility data, where Wetter areas versus drier areas, they have innate fertility differences. So if you are familiar with Hawaii climates, Hilo is a very, very wet and rainy place. And over millennia of being exposed to this wet, rainy weather, we can see that a lot of those nutrients have been leached. So the Hilo soil naturally is more deficient in calciums, magnesiums, and potassium nutrients compared to like this target, this green target where we typically want for our vegetable crops. As compared to like a drier part of the island that hasn't weathered as much, but like in Waimea, it's still a very, very rich soil because a lot of those nutrients have been washed away. Okay, so this is the first part of soil fertility is understanding that different soils have different behaviors and innate fertility in them. So you don't always need to address calcium, magnesium issues depending on where you are in the islands. So the next part of soil fertility is understanding specific nutrients because these are the things that we're trying to make sure that we have enough for our plants. So there's a concept called the law of the minimum where you need to meet certain nutrient demands in order for you to have a certain crop yield. So if you want to maximize your crop yields, you need to meet the most limiting or the most important parts of this barrel, namely the macronutrients. Okay, so these are nitrogen, phosphorus, and potassium they're called macronutrients because they're needed in the greatest amounts for plants in like maybe like the 1 to 2%. And you need to meet these, or else if you do not, then you'll have a significant, I guess, crop yield reductions. There's also secondary macronutrients like calcium, magnesium, and somewhat sulfur that they're not needed as much as nitrogen, phosphorus, and potassium, but still needed in pretty big amounts, or else you'll get some stunting issues. And then lastly, you have micronutrients. So these are these other ones. So there's about 13 to 14 plant nutrients, and the micronutrients, there are a lot of different elements. They're not needed in great amounts. In the plant tissues, you might find them in like the less than 0.1% of the tissue, but they do serve key metabolic functions for the plant, and you'll see yield reduction if you do not meet them too. And a simple way you can tell if you're missing a certain nutrient is by looking at the plant. So this kilo process. So there are some nutrients that they accumulate in the older part of the tissue, older part of the plant, and the younger part of the plant. And the plant, depending on the specific element, they're able to move it around. So if it is a nutrient that is movable or mobile, you'll see that issue in the older part of the plant or the older leaves. So these are primarily the N, P, K, and magnesium. As opposed to if it's a nutrient that is immobile, once the plant absorbs this nutrient in its tissue, it cannot move it around to like the newer growing leaves or the roots. So it's stuck in that part of the plant. So if it's missing in the soil and the plant can't move it around, you'll see the symptom in the newer leaves. So just some pictures showing some symptoms for iron and sulfur, which are immobile nutrients, as compared to nitrogen and potassium, which are mobile nutrients. Okay, you can see the symptoms being either in the younger or the newer leaves or on the older bottom parts of the plant. So some specific details for macronutrient deficiencies. So for nitrogen, you'll see it in the older leaves, but you'll see it turn a uniform yellow. So if you have a plant that's uniform yellow, and you root out other kind of things like water and maybe a disease, most times it's nitrogen deficiency. A similar thing can be said for phosphorus, but you'll see this turning out as more of a dark purple or dark green part of the plant. As well as these plants will be stunted typically if they're not met on an early part of the plant growing period. And in potassium, you'll see the older leaves start to turn like a marginal yellowing of the leaves, as well as if there's any fruit development, because potassium is important for fruit development, you might see stunted fruits. Other macronutrients include calcium. So for this one, you'll see either stunted leaves, the new leaves trying to pop out will be either stunted or crinkled, as well as if there are any fruit, there's a common, I guess, deficiency symptom called blossom end rot, where you'll see it commonly on like solanaceous crops like tomatoes, maybe peppers and eggplants, where if you don't have enough calcium being met, or something in the environment's not allowing calcium to be uptaken in a proper way, you'll see the bottom part of that fruit start to look like it's rotting. It looks like a disease, but it actually might be calcium. Magnesium you'll see the older leaves have this interveinal yellowing, so the veins remain green, but the in between parts are yellow. And then for some of the micronutrient deficiencies, sulfur is kind of like nitrogen on the flip side, but it's the newer leaves being a uniform yellow or kind of pale color. Iron, zinc, and manganese have this interveinal yellowing of the newer leaves. And then boron, it's like a very stunted, kind of brittle part of the new growth, as well as you might see some fruit that turn out very bumpy. So these are common signs of macronutrient and micronutrient deficiencies. Um, so in soil fertility, along with nutrition and nutrients, one of the first things you want to be able to measure and understand is soil pH. So soil pH is what they call the master variable. It influences the physical, chemical, and biological conditions of a soil. If it's, too much on one side versus the other, it could, the conditions could be very unfavorable. So you want it to be in the right spot. So just as a review, if you're not familiar with pH, so pH is um, the abundance or the availability of protons or hydrogen plus ions in the soil. So if it's a lower pH and it's more acidic, there are more protons in the soil. And if it's more alkaline, there's less. Okay, there's more OH minus groups. In soils, it ranges from 1 to 14. So these are just some examples of common household products that, you can get an idea for what is acidic versus what is alkaline. But in soils, we mostly deal with a pH range of 4 to 9. Those are pretty extreme. If you get outside of those ranges, your soils are in a very, very harsh place, and probably need to be amended. Soil pH is important and directly affects the availability of plant nutrients. So you can imagine it if you look at this, if you've ever seen this picture or this video of what happens with a tooth when you drop it into something acidic like soda, how it degrades and erodes over many days. This is kind of how nutrients and the minerals that they come from behave. So if the conditions are favorable, I guess you could say, you actually want those minerals to dissolve because that means it's releasing nutrients into the solution. And if the pH is in a different direction, you can actually have the process go in the opposite, where the nutrients will precipitate into something hard where the plants can um, get those nutrients. So this is just a simple diagram showing the different nutrients and their relative availabilities at the different pH levels. And we can see that at least for most nutrients, they don't always align perfectly, but to maximize majority of the nutrients, you want to be at this pH 6 to 7 range. Typically, you can still grow plants, 7.5, or you can maybe grow it a little bit less than 6, but you want to kind of stay close to this range to make sure that you're having the most nutrient availability as possible. There are some plants, like we said, that, most of them they do like that 6 to 7 range. So a lot of the vegetable crops like cabbages, eggplants, tomatoes, even lemons and citruses. You do have some fruits that can handle a little bit more acidic pHs like bananas. And then, but you do have some exceptions to the rule. So things like pineapple, blueberries, even camellia tea, the type that we drink, those all require acidic conditions. So if you are growing any of those three crops, you typically need to either make sure you have acidic soil, or you might actually manually have to acidify your soil because those crops do better under those conditions. So one interesting thing that we deal with in tropical soils is because our basalt minerals have a lot of aluminum oxide in them. If the pH is too acidic, that aluminum mineral will actually dissolve and release aluminum ions into the soil, which are toxic to plants. So anytime you get the pH less than maybe about 5.5, you'll see that there's a lot of aluminum ions in the soil solution, and they impact plant roots, and you'll get stunted roots. And with stunted roots, we have stunted plants that may eventually die. So to avoid this issue, all you have to do is simply make sure your pH is at least above 5.5. So if 5.8 is a safe range, and the aluminum is now precipitated into a mineral, not being in the solution, and the roots can grow healthily now. That's typically for our tropical soils. So if you want to increase soil pH, one of the simplest things you can do is add some kind of liming material. So you might hear the term lime and think of fruit, but it's actually a agricultural limestone. So this can be calcium carbonate, it could be dolomitic lime, something that has a neutralizing ability for those protons in the soil solution. Um, there's a lot that can be said about it. There's coarse ones, there's fine ones. You don't wanna get it too fine or else it can blow away in the wind. So something that is maybe like 80% fineness to 90% fineness should be good. So it's not too fine where it will blow away. To find out how much you need to add, we have different liming curves available on the CTAHR website. There's a publication called Soil Acidity and Liming where there's different curves for different soil types. So if you're able to find your location, you can use that curve. If not, there's a generalized curve that I also represent here on this graph, on this slide. Or if you have a starting pH of 5, for example, and you want to increase it to 6.5, you would use this curve where you would, start off on the graph and trace down on the x-axis where you are for your where you are and where your target is, and you would subtract the difference. So, our target is 4 tons, where we are is half a ton. So we subtract the two, and we know we need about 3.5 tons of lime per acre. And another important thing is if it's a big area and in the field, um, experts typically recommend you multiply this 3.5 by at least a factor of 1.5 because the field conditions are not like a laboratory condition where these graphs are made. So this might actually be closer to like 5 tons in reality. There are also curves if your pH is too low. There's you can also add elemental sulfur. So this is different from sulfate. So sometimes we work with individuals and they think if you add calcium sulfate that has a acidifying property, but it doesn't. It's not a strong acidifying agent. What you want is pure elemental sulfur. So it's just the S element. We have curves available at least for andisols that you'd find typically on Maui and Hawaii Island, where you can use this curve in the same way to figure out how much pounds of sulfur you need. But this is primarily for, farms or growers looking into like blueberry, tea, or pineapple production. Yeah, so might not be as common. Also, if um, the farm uses urea and ammonium fertilizers commonly, and also over time, these fertilizers, because when this nitrogen ammonium form is hydrolyzed, it releases protons, H plus ions into the soil. So if you keep using these over time, you'll increase that hydrogen ion, so you'll be naturally acidifying soil pH. So over time, you can see in this graph, at the highest nitrogen ammonium nitrogen fertilizer rate, it drops almost by 1.5 units of pH. So this can be a tool if you want to acidify a soil, but also keep in mind if you do use these fertilizers and you've never checked your pH over time, it might be a good thing to do because you don't want to get below that 5.5 pH level where you might get aluminum toxicity. Okay, so the next part is fertilizer management. Now that we've understood a little bit about soil types here, the importance of pH and also nutrients, now how do we manage fertilizer appropriately? So it's all about the right type, the right place, and the right time. Because as we know, if you under apply fertilizer, you'll get, deficiency symptoms, your crop won't grow well. But, there is a negative aspect of over applying fertilizer. Not only is it wasted money because the plant can only absorb what it needs, but if you nutrient load your soil and, like we've been getting over the past couple years, a lot of rain, or maybe there's a broken irrigation pipe and it washes a lot of soil off your property, that nutrient is now off your site, so that's wasted money. But that water, that soil, nutrient-rich soil, uh, water eroded soil gets eventually into the waterways and the oceans, where it's been found that nitrogen pollution can cause like things like tumors on top of turtles. So to be a good environmental steward and care for other parts of our islands, our INA, we want to make sure that we don't over apply fertilizer also. So for the right type, it's easiest to start off with maybe the macronutrients. So knowing what nutrient does what in the plant. So as a start, I like to teach like the reverse alphabet. So rather than NPK, I teach PN and K. So, as a plant is small, you want to make sure it has good roots to grow. So you want to make sure that you add phosphorus because phosphorus are for root growth. And once that plant grows a little bit more and you're trying to get it to grow stems, branches, leaves, then you want to make sure you're having enough nitrogen, okay, for the shoots. So P for roots and for shoots. And if it is a fruiting crop, such as like for tomatoes or oranges, you want to make sure you have enough potassium in there because potassium is important for fruit development. Okay, so as a simple teaching tool for at least the macronutrients, the three most important ones is P for roots, N for shoots, and K for fruits. And this can also be utilized in a simple fertilizer schedule. So, kalo is a very important plant here in Hawaii, and there are certain ways that you want to make sure that you fertilize if you do grow this crop. So, if you do need to add fertilizer, the first thing you do before you plant, so in the pre-plant stage, is make sure you add all your phosphorus, calcium, magnesium, and if you need to, micronutrients into the soil before you pre-plant because those are kind of difficult to get into the root zone after the plant is starting to grow. Um, but once it is, once you have add those nutrients for root development and now it's growing shoots, you might switch over to a nitrogen-rich fertilizer, such as like urea or 2100. And this is to maximize that stem and leaf production. And when you do add this, make sure you add it in splits. It's not good to add it all at one time because, that fertilizer it might move around in the system and be lost. So yeah, try to add your end fertilizer as a split. And it grows, and we all kind of know like about like the 5 month, 6 month period, you kind of stop it off if you want to grow for corn production. And because the corn is kind of like a fruit of the kalo plant, this is when you might switch over to a more potassium-rich fertilizer to make sure that you're getting good corm development. Okay, so this is just a simple way to make sure or example of how to use the right type of fertilizer for a kalo example. For the right place, right by the plant is one of the best ways you can do it. Sometimes, depending on your situation, you might have to broadcast it broadly, but if you're able to get it right where the plant is growing, it can be the best. And one of the examples to show that is this term called phosphorus fixation. So, oxide and volcanic ash shows, like the ones we have here in Hawaii, whenever you add inorganic forms of phosphorus, so, 30-10-10 or something like that, that phosphorus, if there's sites on the oxide surface, it'll get bound to that oxide mineral so tightly that the plant can't access it. So to get around that, one thing you can do is ban application. So you'll see that when you add the fertilizer, directly as over the banded row where you're planting, you actually get more phosphorus in solution for the plant. The other alternative is if you do use organic fertilizers, organic forms of phosphorus, like manures, those types of things, they don't have the capacity to be fixed as much. So either um, management practice can help you get over this phosphorus fixation we have in our soils. Now, what about if you grow an orchard? Because it's very difficult to incorporate fertilizer into the soil if you're having fully matured trees because you don't want to damage the roots. So one thing you can look at is we have organic forms of fertilizer, for example, like blood meals and bone meals that we like to use, but you can, liquefy that and turn it into liquid fertilizer. So whether it's this organic form or also inorganic forms like urea and other things that's solubilize very easily, that's um, one way you can do it too. And once you've dissolved it into a liquid form, you can either inject it through the line or you can drench it next to the trees, a lot of different ways to do it. But this is just one example. But if you are interested in that, this liquid fertilizer made from tankage or some other organic amendment, we have material on that through a liquid organic fertilizer project. So you can either look at this video at a later time, or if you Google CTAHR and the term tankage, you'll find a lot of research that has been done from our different CTAHR researchers and team members. And then lastly, the right amount and right time. So this is a very colorful and busy graph, but I promise you it's very useful. So this is an example of a project that was done by a graduate student, where on the left-hand side, you'll see the farmer practice. So this farm that was growing cabbage, they, you know, they grew their plant, and this dark solid line, represents a plant growth. So it has a certain yield. And the farmer at the beginning, they split fertilizer applications, but then, a lot of that fertilizer was added in the very beginning. Okay, when the plant is still very small. And plants, they're kind of like people where, a baby, they're hungry, but they don't eat as much as like a mature person, or like a, a teen going through their growth spurt. Yeah, so they only need a little bit in the beginning, but they added a lot in the front. And you can see they got their desired yield. But using what we know about soil science and plant sciences, we know that we can maybe taper off in the beginning and focus that, more towards where the plant is growing the fastest, the steepest part of the curve. So this professor and the grad student, they did that, where it's, a lighter amount in the beginning and a heavier amount right when that plant is starting to spike, because the fertilizer, it's not immediately available. It takes a couple of days, but they targeted that and they got the same exact yield, but, with reduced fertilizer. So this showed that, if you can time it right with the right amount with the right timing, you can save on your fertilizer costs, but still get without reducing yield. Again, just, this number is from 2018, but I think right now the fertilizer cost, it's about the same, cost as a pound. So they actually nowadays you might be saving close to like $350 per acre doing this method. So to know what is needed, one of the best things is to do soil testing first, okay? Because you don't know until you test. So this is an example of a couple of farms that we've helped do soil testing. And this one farm in the beginning, it kind of got everything that they needed. The phosphorus is just right, the pH, the calcium, magnesium is a little high, but not too bad. And then we have another farm that over years they've been adding blended fertilizers, so triple 20s, 30-10-10s, and they don't deviate from that. And you can see that years of doing that, they've actually accumulated excessive P. So if a storm event happens and this nutrient-rich soil runs down into the oceans, that can pose that problem that I showed on the earlier slide. Yeah, so this is why it's important to be able to test, because maybe they don't have to add that triple 20 fertilizer. They can just add a fertilizer that, you don't need phosphorus, calcium. They just have to add something maybe with just nitrogen. So for Hawaii, we're lucky we have a few testing options. So one is, it just opened up recently, but the our Agriculture Diagnostic Service Center just reopened their soil testing lab. So this is one option if you want. There's certain protocols involved, at least right now, where you need to work either with extension office or extension center to submit it, due to some shipping limitations if you're on other islands. So this is one option, and with the packages that it offers. But other ones that people commonly utilize here in the islands is, one is called crop nutrient solutions that work through Brookside Labs. So that is one option. I know some individuals on Big Island, they actually work through a chemical company, Nutrient Ag, that sends their soil tests to Precision Agri Lab. So that's another option. And then the one of the other options that just became available is this Makali'i Metrics. So they're another lab found on Oʻahu, that just opened, and that is another one that offers a suite of surfaces for soil testing. So if you're interested in soil testing, any one of these labs, and there may be a couple more too, but these are the most common options. So if you're collecting soils, first contact the lab just to make sure they don't have any specific protocols, but typically this is the general structure is, one, you want to make sure you're sampling at the correct depth. So making sure you're just getting in the root zone of the plant. So if it's a vegetable, the roots grow to about 8 inches, 10, 12 inches. So as long as you're getting that soil sample at that depth, that should be sufficient. And then for trees, same thing, like a lot of the feeder roots are on the t top surface, so as long as you get that one, that's okay. But um, there's also another recommendation where you get that one plus one that's at least like about a foot or 2 feet deep to analyze what the nutrient status is in that lower root zone. So once you've done identify that and have your appropriate shovel or trowel, you don't wanna just collect in one spot. So you wanna go in a zigzag pattern across the field to make sure that you're getting a representative sample over the whole, plot that you're gonna be growing. Make sure you're not collecting it right after you fertilize or soon after because you might be spiking the sample and get a false reading. But with your multiple sub samples that you take, put it into like a bucket or a big bag and mix it up very well, homogenize it, and then put it into that smaller um, container or bag that you're going to be submitting to the lab. And when you submit it, you'll be getting a soil test result back that might look something like this, where they'll be giving you your analysis result in this is indicated in a white column and then the target value. So this is where you might specify a certain crop like cabbage or something like that that has known target values for nutrients. So that's here in the green. And at least for our Hawaii, I guess recommendations, we utilize like an article like this that has some, I guess, historic data for calcium, phosphorus for different soil types. So looking at this soil test, you can see that if it's not indicated, highlighted in red, we know it's sufficient. So like the phosphorus, it's above that target value. Calcium's above that target value too. So it's sufficient and no fertilizer for that nutrient type is needed. But we do have some that is highlighted in red, that might indicate a deficiency symptom and may require some fertilizer needs. But for micronutrient, some crops are more resilient, and sometimes you might not need that micronutrient unless you see a deficiency symptom on your plant. Yeah. So at least for this recommendation and soil test, only nitrogen fertilizer with suited applications and possible like micronutrient amendments were needed because everything else was adequate and sufficient. And it's important to find this out because, like we said, we want to be good environmental stewards, make sure we're not polluting the oceans and waterways. But also, fertilizer is becoming more expensive. So if you do not need PRK, you might save money. So for example, like a bag of triple 20, it's about like $120, $140 for 50-pound bag from certain sources. But if you don't need PNK and you just need nitrogen, which is the sole ingredient in urea, you'll find that's just a $50 for a 50-pound bag. So you'll save a lot of money and also help the environment. Okay, so this is important of soil testing. So now that we have our soil tested, we know what we're missing. Now it's to understand the specific fertilizer types. So first part is to just understand a really basic but common fertilizer bag. So oftentimes you'll hear or see three numbers. So throughout this presentation, you've been hearing me say triple 20 or 10-30-10 or something like that. And that represents the nitrogen, phosphorus, potassium, or the NPK of that fertilizer type. So you can see it here in these boxes and the arrows, which number represents which one. So for nitrogen, it's straight elemental N, but for phosphorus and potassium, it's the oxide form. So for this one, the soil labs, they'll take this into account when they give you a recommendation. But if you do some kind of calculation on your own, just make sure that you keep this into account and you'll need to do a conversion factor first. And some fertilizer bags, they also have other nutrients on them. So it might be indicate there's iron or calcium on there. So just take note of any kind of labeling on the bag as well as on the back. They might give a deeper breakdown on the percentages of those other nutrients too. There are two common categories of fertilizers. So one is inorganic fertilizers. So these are ones that are typically the synthetic ones, or quote unquote, like people think is like chemical fertilizers that are uh, simpler forms. So a common one is urea. So it's a very simple molecule that in oxygen-rich soils like we do have here in the tropics, they break down very quickly into ammonium and nitrate. And you can see these molecules, they're very simple. In a simple way, you can say it's like two letters because it's very easy for the plant to uptake and it's readily available. So if you need a quick boost for your plant, inorganic fertilizers are a very important fertility tool. But because they are simple, they also can be lost very easily to the environment. So if it's raining very hard, they leach very easily with the water through the soil profile. If there's lack of oxygen, microbes actually can steal that oxygen from the nitrate molecule and use it up, and the nitrogen is lost as a gas. So it can be acted upon very easily. So it needs to be, you know, same thing, the right time, the right amount, the right place to make sure that it's not being wasted. Here are just some examples of common inorganic fertilizers. So you can see some of the N, P, and K that we have here. Some are so, uh, I guess, consist solely of a nitrogen or solely of potassium, but you do have some that are combinations. So a common one is if you do need calcium and you do need nitrogen, an option might be calcium nitrate, or something like that. Okay, so these are just this you can find easily on like our CTAHR website, and other websites have them too. But just letting you know that for N, P, and K, but also calciums, magnesium, sulfurs, and the micronutrients, there are a lot of inorganic fertilizer options available. The other flip side is organic fertilizers. So these are also common. You might hear about them like the fish meals, the blood meals, manures, whatnot, that are each rich in their individual specific elements. So it might be nitrogen, phosphorus, potassium, that they're a better source of that nutrient for. But you might notice that these percentages are oftentimes a little lower. So compared to like urea that is 46% nitrogen, there's there's not too many organic fertilizers that you'll find greater than 10%. Most fertilizers that are organic are either 10% if it's a rich nitrogen containing fertilizer, or it might be closer to like 5 or 6% if it's a moderate one. There are some exceptions, like for sulfate of potash. That is one potassium source that is actually very rich, and it's a good source of potassium if you do need it. Organic fertilizers, they are more complex molecules because they need to be broken down by microbes first to release those nitrates and ammoniums, for example. So they need to be mineralized. So if you need a quick boost, it can be challenging because it is a slow release fertilizer, but that is also a potential advantage because if you don't want it to be lost as quickly, that nutrient is still protected by that organic molecule and might not be acted upon by other environmental factors as easily. So it can be a good and a bad. And also I mentioned before, a lot of these organic fertilizers, they don't get fixed like that phosphorus, synthetic inorganic phosphorus does. So that can help you get around those challenges too. For calculations, this can be a tricky one. So reach out to, your extension agent or another agricultural professional if you do need help with them. But just keep in mind that, there are different calculations involved. So basically, if you have a lower nitrogen percent on your material, the slower the release. Okay? And to calculate how much you need, say this is our target is what is required by the crop is 200 pounds N per acre. We need to divide that number by the content of nitrogen in that fertilizer. And then if it's in organic form, also its release percentage. So you can see on the urea example, because theoretically 100% is immediately released or available. We divide that 200 by 0.46 as a decimal, and we need about 435 pounds of urea to meet that 200 pound need. So, it's a little bit more, but it's not too bad compared to the others. So you can see in the feather meal, it's a lower nitrogen percentage, as well as it because it is organic, it releases it at a slightly slower rate. So to meet that 200-pound N per acre need of the crop, we actually need to add about 2,000 pounds or 2,080 pounds of feather meal per acre. And then for compost, you can see it's a very low N and it releases it very slowly. That to meet the same need, you'd need like 50 tons per acre. So that's why typically these low N materials, if you're trying to meet a nitrogen need, like things like compost and mulch, it's more for a soil conditioner or some other use rather than a nutrient need. So one of the last topics I want to talk about is the importance of organic matter. So a lot of these things I've been maybe discussing have been more inorganic or some mention of organic fertilizers, but for our tropical soils, organic matter is very, very important. And the reason why is we take this example. So there's an island in the Federated States of Micronesia. It's called Pohnpei. It's a very rainy area, very high rainfall, and as we expect, it has, a lot of leaching and very acid soils like we discussed in the earlier part of this presentation. So you can see on this map, a lot of the soils, especially in the interior of the island, are like 5.5 or less than 5.5 pH, which we'd expect to be very challenging for crops. Also to note that, a lot of these places, they don't have easy access to affordable fertilizers. So oftentimes they don't add fertilizer when they grow things. So you'd expect a place that has leached acid soils with no fertilizer should be having a lot of challenges growing any kind of plants or crops. But when you go there, you see there's an abundance of plants, ulus, kalo, niu, that feed them and have been feeding them for millennia. And the key is organic matter because they don't till and break up that organic fraction that and it gets released into the air and lost. It's been intact for millennia. So that's the key for a lot of these tropical systems. So what organic matter influences is soil health. So it's the ability, continued capacity of a soil to function as a vital living ecosystem that sustains plants, animals, and humans. And there's four main principles. And the main thing to get from this is that, it's all about preserving organic matter in the soil or things that are organic, like animals, and fungi. So anytime you can maximize continuous living roots through like things like cover crops or perennial crops, minimize disturbance, so maybe reduce tillage, or tilling only in specific rows that you're going to be planting, maximizing soil cover as much as possible. So this is once again with maybe green manures or mulching, and then maximizing biodiversity from like a macro scale to a micro scale. All these things help to preserve organic matter and in turn soil health. And organic matter is important because, one, it's a nutrient source. It releases macro and micronutrients like these feather meal and bone meal fertilizers. But that organic molecule, it's loaded with negative charge, which is important for holding key plant nutrients like calcium, potassium, magnesium. So if the soil is low in negative charge, by adding organic matter, you boost it up. As we said before, organic forms of nutrients, they have less P fixation. And then for a magical property is, like we saw in that previous slide of Ponpe, acidic soils, especially in the tropics, they shouldn't be having aluminum toxicity issues. But the humus or organic matter molecules, they magically chelate or claw and capture aluminum ions in the soil and make it inactive to the plant root. So that's one of the beauty of maintaining organic matter in your soil, especially if you do have acidic soils. Organic matter also improves aggregation or, anytime soil particles clod together, so, lack of a better word, dirt clods, that's a good thing for the soil because that also improves drainage and those aggregates, they're packed, although they look like a big rock, they have a lot of micro surface area inside of the interior of that aggregate that can hold water too. So it's good for drainage, but also good for water retention. So you can see here in a simple demonstration where you have an organic matter rich soil that had cover crop growing on top of it, um, and had that cover crop incorporated. So you can see better aggregation and aggregate structure. So when you pour a simulated rainfall event on top of it, all of that water passes nicely to the profile rather than leaching off, compared to the bare ground where it's void of organic matter and that root structure. So it's very compact, and all that water just washes right over, potentially into the ocean. So this is another very important reason why organic matter and living roots are important for a soil. So here are just some simple examples of ways to add organic matter into an agricultural setting. So cover crops. So these are plants you can grow, things like sun hemp, sorghum, pictured here, cowpea, buckwheat that grow quickly, but you can till them in and add a lot of organic matter into the soil, so carbon, but they also might serve other benefits too, like maybe nematode control. So here are some resources like a cover crop calculator for being able to calculate nitrogen when you do cover crops, and also an article that we wrote that showed that yeah, when you do you add and incorporate certain cover crops, you actually can reduce your fertilizer inputs because they do add nitrogen to the soil too. And another one you can consider too for increasing organic matter is compost. So, when you add it into the soil, we have projects that showed, you increase your soil health score without and you actually kind of increase yield in certain um years that you incorporate it. Um, it's a short-term study, and a longer term you might see greater benefits, but in the short term that we did study it, we showed that for a lot of these soils that have start off with low soil health, adding organic matter increases it over time. So that was a quick introduction to Hawaii soils and also tropical soil health. My name is Josh again, and if you have further questions, you can feel free to email me or you can ask it now. But thank you.